Hello everyone, and welcome to a series of short videos in which we are going to be exploring some fundamental concepts of the physics of semiconductors. There will be 5 videos, each of them explaining one aspect of semiconductors, starting with the concept of effective mass. We will continue with Hall effect, then pure semiconductors, doped semiconductors, and we will finish this series with the p-n junctions, which is the basic building blocks of modern technology. We have interesting topics to discuss ahead, so let's not waste time with this introduction and dip our toes into the concept of effective mass. And to do that, I'm going to introduce to this little guy, Robert. Robert weighs about 90 kilograms and he likes running. He notices that when he runs, his kinetic energy increases, and this increase is parabolic and independent on the direction. This can be expressed as a function of momentum in the following way. Now, one day he wants to measure the value for his inertial mass, and to do so, he applies a known force to himself and studies his own acceleration. Now, to do so, he knows that the velocity is the derivative of the energy with respect to the momentum, and the acceleration is the derivative of the velocity with respect to the time. Now, unsurprisingly, he finds that his inertial mass is also the mass that appears in the weighted machine. Now, why on earth am I saying all that? Well, electrons has a mass of about 1.6 10 to the minus 19 kilograms. But when they live in semiconductors, the inertial mass can be different to this actual mass. And to illustrate this, let's take silicon. The dispersion of one electron in this band is approximately parabolic. And we can basically apply the same mathematical machinery that we saw before to calculate its inertial mass, because it turns out that this is a very useful concept to study transport properties like resistivity. Now, we calculate the acceleration, and we calculate the force and the ratio between them, which is essentially the reduced Planck constant squared divided by the second derivative of the dispersion with respect to the wave number. Now, this brings a question on the table. Can we actually extend this concept for all the electrons? For example, this electron in this band? The answer is yes, but there is a caveat. The mass then is negative, and actually makes sense, because as we increase the velocity, the energy decreases. Now, the second point is that normally there aren't just a few electrons in this band, but rather there are many, many electrons. The band is actually completely occupied, only depleted by a handful of electrons. Thus, according to this, in a normal scenario, we need to study the motion of almost all the electrons in this band, each of them having a negative mass. The good news is that we can rephrase the problem. And instead of studying a lot of electrons in this band, we can actually study the motion of the emptiness, or these quasi-particles, or this bubble, often referred to as a hole, that can be related to the corresponding electron by having positive mass and positive charge. Okay, that was a short story I wanted to tell you today. But before finishing this video, I'd like to try a short exercise. Compute the effective mass of an electron in an atomic change. I'd like you to try this exercise. I'll give you a few seconds, and please use the dispersion provided here. Okay. For those who solve it, congratulations. And for those who just want to enjoy the show, we just need to apply the second derivative of this formula and insert it into the expression for the effective mass. This exercise is actually not very hard, but it allows me to speak about what normally happens within a band when we change from an electron-like behavior or electron-like particles to hole-like particles with negative mass. Because the second derivative of the dispersion is normally continuous. And when going from positive to negative, you have to hit 0. At that precise point, mass, or the effective mass, diverges. And this can be tracked in an experiment. But wait a minute, in an experiment? But how can we actually tell whether we have holes or electrons in an experiment? Well, this is precisely the topic of the next video, the Hall effect. Until next video, goodbye.